Our next questions are from GATE 2014 heat transfer, each for 2 marks. Actually, we will solve in this 3 questions. Question number 33 first. A brick wall of 20 centimeter thickness has thermal conductivity of this, and insulation of thermal conductivity of this is to be applied on one side of wall so that heat transfer through the wall is reduced by 75%. The same temperature difference is maintained across the wall before and after applying the insulation. The required thickness of the insulation is. So let's start with the solution. So you can see here, this is the initial condition. We have a wall having a temperature difference is delta T, that is T1 minus T2 we can say, and this is the thickness 20 centimeter, and thermal conductivity is given as 0.7 watt per meter Kelvin, right? The equation will be given as Q is equal to delta T up over L by K. L by K is actually the resistance. This is the resistance, you know that, right? So Q is equal to, Q will be delta T upon L is 0.2, that is in meter, 0.2 in meter divided by 0.7, since it is 20 centimeters, so it will be, so actually we will get Q is equal to 7 by 2 delta T, where Q is the heat flux. So I am getting the heat flux is 7 by 2 delta T in first condition. But in second condition, what we are going to do, we are doing a insulation with thickness X and having a thermal conductivity of material 0.2 watt per meter Kelvin, and temperature difference is delta T, right? Same temperature difference, since they have already told us that we are applying the same temperature difference. So for this we are having two resistances are here, one is for slab, one is for wall, or one is for insulation, right? So delta T upon 0.2 divided by 0.7 L by K, plus for this L by K is X by 0.2. there is no problem with this. And they have given one more thing, heat transfer will reduce by 75%. So we can say that this is the initial heat transfer, this is final heat transfer, so it will be Q1 minus Q dash upon Q into 100 is equal to 75%, right? After solving you will see Q dash is equal to 0.25 Q, right? Q dash is this, and we have calculated Q initially, that is 7 by 2 delta T, right? So from this we will put all the values. After solving we will get X is equal to 17.17 centimeter. This is the final answer, right? Now our next question is question number 34. An oil with a flow rate of 1000 kg per hour is to be cooled using a water in a double pipe counter flow heat exchanger from a temperature 70 to 40 degrees centigrade. Water enters the heat exchanger is this and leave at this. The specific heat of oil and water is given. The overall heat transfer coefficient is given. The minimum heat exchanger area required for this operation. So let's start with the solution. This is the temperature profile, right? Hot fluid temperature decreasing from 70 to 40 and cold fluid temperature increasing from 25 to 40, and it is given as it is a counter current flow. So LMTD is equal to 30 minus 15. How? Since you can see temperature difference for this is 70 minus 40 is 30, it is 30, and 40 minus 25 is 15, that is 15. 30 minus 15 upon ln 30 by 15. After solving we will get 21.64 degrees centigrade. This is the LMTD. Now heat transfer rate, Q is equal to MC delta T, right? M is oil flow rate is 1000 kg per hour and specific heat for oil is 2 kilojoule per kg Kelvin, right? From this 1000 kg per hour into 2 kilojoule per kg Kelvin into 70 minus 40 for oil, we will get from this 60,000 kilojoule per hour. So we will convert it in kilojoule per second, 16.66 kilojoule per second. We will divide it by 3600, so we will get 16.66 kilojoule per second. Why I am doing this, since we want to convert it in kilowatt, so it will be kilowatt, since joule per second is a watt, right? So heat transfer rate from HE will be given as, from heat exchanger will be given as Q is equal to UA LMTD, and we know that we have given Q is 16.666, we have already calculated as, right? So and we have given U, that is 0.2 kilowatt per meter square Kelvin, into area. A is the area of heat exchanger, and we have calculated LMTD already, right? After solving we will get area is 3.85 meter square. This is the final answer. Now We have next question, question number 47. The bottom face of the horizontal slab of thickness 6 mm is maintained at 300 degrees centigrade. The top face is exposed to a flowing gas at 30 degrees centigrade. The thermal conductivity of the slab is 1.5 watt per meter Kelvin, and the convective heat transfer coefficient is given at steady state. Temperature of the top surface is. So let's start with the solution. Plate. This is the horizontal plate, and bottom is maintained at 300 degrees centigrade, and the thickness is 6 mm, right? And upper surface temperature, I am assuming it T, and temperature of the air is 30 degrees centigrade. So at steady state, heat transfer from here to here will be equal to heat transfer from here to here, right? So heat transfer from this slab will be 300 minus T divided by L by K. That is a resistance. L by K is resistance, and it should be equals to T minus 30 upon 1 upon H, right? In case of convective heat transfer, the resistance is 1 by H, so it will be T minus 30. No problem with this. We have given L, thickness of this slab is 0.006 meter divided by 1.5, K is given as 1.5, and T minus 30, and we have given H is 30. So our final answer is T is equal to 271 degrees centigrade, since we have put all the values in degrees centigrade, 300 degrees centigrade, 30 degrees centigrade. So the top surface temperature will maintain at 271 degrees centigrade. This is the final answer. So thank you. Please make sure to like, share and subscribe my channel. Thank you.